welcome to join this very specific and special forum today. It's our great honor today to have the awardee of the Presidential Science Prize of Taiwan in 2021, Professor Sunny Chen, to join this forum. On my left side, everyone can see Sunny is sitting here. Sunny, you want to wave your hand to everybody? And on my far left hand side, Dr. Untitled. Dr. Tao, want to wave your hand? Dr. Tao also would join us today, especially in the second half of the event, which is the Q&A with all the participants online. All right, without further ado, I guess everybody knows pretty well that Sunny achieved greatly in the research as well as in his life. So the event today is not only to deliver the scientific achievement of Sunny, but also give everybody the life story of Sunny's career. So the events will be basically in two halves. The first half will be the video plus the presentation by Sunny. Then after that, we will take the photos, and everyone join us online will be part of the photos. And after photo taking, we'll move to the second half, which is the Q&A. And I like to remind everybody that each of you would have the opportunity to raise your question through the chat box. You can text your question in the chat box, and we'll collect all the questions from you guys. And I will be responsible for asking questions to Sunny and Dr. Tao. So they will be very happy to answer the questions from all of you. And since the participants today will be mostly from young generations, so I guess you will have a lot of curiosity about how the scientific career of Sunny was achieved, and how Sunny perceived the future generation of scientists, especially how to cultivate your own career. So this will be the focus of the forum today. Without further ado, let me introduce the host of this institute, Dr. David Wu, who would give us a little bit introductory to Sunny. Also, as the host of the institute, he also like to meet all the participants online. So let's switch to Director Wu.
Hey, thank you very much, and good afternoon to everybody. And first, let me just say it's a real pleasure and honor for me to host this and to host this event and introduce academician Sunny Chen, who's been so influential in not just the Institute of Chemistry, and in the field of science internationally, but also specifically for the impact he's had in Taiwan. It's great to see so many young people here. Let me just say right off that I know that this means a lot to Sunny just because I've talked to him before, and he's talked about how important it is to him personally to, in terms of the impact he's had to mentor young scientists. And that's really one of the most meaningful things that can happen in an event like this. And even though we're meeting online, I hope one day that we can gather more in person for more direct contact. But let me just give you a few words just to introduce Sunny's background. So Sunny is from the United States, the Bay Area, and he did his college degree and his PhD at the University of California in Berkeley. He went on to do his postdoctoral research at Harvard, he after a few years at the University of California system, he actually spent most of his academic career at Caltech, rising through the ranks quite rapidly. During that time, he worked on some very important problems really on the fundamentals of biological processing systems and molecules, including things like interactions between nucleic acid molecules, also membrane-bound proteins, which is a very challenging program, kind of a holy grail of trying to understand biological function at a molecular level, including problems involving cellular respiration, which is a basic problem, as well as starting in Caltech, but also really developing here in Taiwan, the problem of looking at biological catalysis of methane into methanol, which is very important today for carbon, for management of carbon. So he'll tell you more about that, but let me just mention in terms of his impact in Taiwan, he came back to be the director of the Institute of Chemistry and eventually a vice president of Academia Sinica. During that time, he really reorganized or reshaped Institute of Chemistry from traditional divisions into intellectual thrust areas that really are very vital even today, materials, catalysis, and biology. And of those three, materials is more established, but catalysis is a new thrust, in particular kind of a rational approach, and chemical biology. These are really far-reaching kind of fields that even today have a lot of promise. So, I think he's had a big impact. And even when I look at myself, I look at the people around, you can see the many threads of the decisions and advice that he's given and the hirings that he's done that's really had a big impact on the Institute and in science in Taiwan. And finally, I should just mention, I think in terms of mentoring young people, he was also the founder of the Taiwan International Graduate Program. So, that's really part and parcel of the whole scientific enterprise. And I would just end by encouraging all the young people here to really take this opportunity to, share questions, your thoughts, ask questions of Professor Chan. And, because one of the beautiful things about science is it's not just an individual pursuit, it's also about a community. And when you're reaching out into the unknown, which is what this is about, you can learn a lot from, those who really paved the way before us. Okay, so without any further ado, I would pass it back to the rest of the ceremonies here.
Thank you so much, Director Wu. We wish someday very soon we can sit here together and celebrate Sunny's achievement one more time. As David just said, Sunny was the founder of Taiwan International Graduate Program, TIGP. And I was really lucky to take the legacy of Sunny to host this program, which is really successful after 20 years of establishment. All right, so the next important thing is the photo taking. Sorry, I take it back. The next important thing is the video. The video which shows the great achievement of Sunny. And that was well done and very beautifully summarize Sunny's career. So let's take 5 minutes to view the video together.
And I don't believe in short-term impact. I believe in long-term impact, like Beethoven's music. I mean, his long-term impact. My favorite composer in music is Beethoven, because he writes a variety of music, right? And his music is very creative. Creativity is the most important part of my outlook. I'm intellectually curious of what the truth is, and I like to work on problems that nobody knows anything about, if possible, and I am the one who actually get the answer. The only methane oxidation protein that I work on the last 25 years, that has impact on the well-being of humans as well as society. we learned the chemistry so you could develop the catalyst, all right, to reduce the carbon emissions. I'm just interested in solving a problem, understanding, all right, is a challenge to my intellect. Science is a challenge to my intellect.
所以他在这个科学界，不管是在台湾，在美国，他都很受大家的喜欢，也更尊敬。他整个在学术方面从头到尾是一贯的一气呵成的年纪已经这么大了，还是锲而不舍，把他这个最重要的问题完成。
Creating a research team, managing a research team to help you go from point at the beginning to the end, that's the most difficult part. All right, and recently in 中央研究院, we discovered the correct structure, and I was very pleased because we had predicted everything already.
他到台湾也还做非常多的研究，然后他真的还要把他的美国的人脉带到台湾，然后让我们学生接触到很多国外的老师，他也帮台湾很多学生接受到国外去继续做研究，然后他自己在台湾的研究还做得非常非常的好，就是每年的这个 productivity 都非常非常好。
对科学的执着，对，他是一个很聪明的人，很多事情他很快的可以抓到事情的重点，去 catch up 这些事情。那他知道这个点是这个时候，那他会非常执着去答案这个。他认为说我相信的是对的，然后他会去证明说我所做的事情是对的。也因为这样子可以把我们带得很远，可以走得很前面。我想这个是一个非常非常重要的事情，这个就是执着。
I just brought the idea here, sowed the seeds. I came to Taiwan, all right, at 62. And of course, Ron Lee gave me the opportunity to come here. But I didn't have to accept, right, when he invited me. But I came mainly because I felt it's time for me to pay back, right, to society. I came here to infuse a research atmosphere. I want to discover the truth. And if the truth leads to technology, which eventually lead to something that was important for society, great. I do science so it's going to have influence.
All right, as all of you have already viewed this beautiful video, Sunny is not only a scientist, but also the educator, and plus Sunny is such a humble citizen to the society of Taiwan. Next, let's welcome Sunny for his well-prepared lecture. And this lecture would definitely inspire the young generation. So I would switch the camera to Sunny. So everybody, please listen to the lecture carefully.
Thank you, Dr. Moon. And thank you, everybody, for all those kind words. Before I start, let me first thank the Presidential Office of Taiwan and the Ministry of Science and Technology for the Presidential Science Award, the Presidential Science Prize. I also like to thank the Chinese Association for Industrial Technology Advancement for sponsoring this event. And for Academia Sinica, the Office of International Affairs, for hosting it together with the Institute of Chemistry. Without all that, I wouldn't be here. Thank you. Thank you for your help. Well, as a scientist, I have lived through an exciting era. Here are just a few developments that have inspired me during my lifetime in 3 disciplines: physics, chemistry, and the life sciences. In physics, the development of quantum physics, Einstein's general theory of relativity, theory of elementary particles, discovery of the quarks, discovery of the black holes, evidence of the universe expansion, detection of gravitational waves, discovery of superconductivity, invention of the transistor, invention of the laser. In chemistry, the nature of the chemical bond, relating chemical thermodynamics to statistical physics, theory of reaction rates and prediction of chemical reactivity, including roles of catalysts, chemical synthesis of natural products and polymers, discovery of ferrocene, synthesis of xenon hexafluoride and noble gas compounds, development of asymmetric synthesis and organocatalysis, understanding photosynthesis, biological nitrogen fixation, oxygen reduction, methane oxidation, and water splitting. All that during my lifetime. It's quite amazing. In biology, it was Watson-Crick structure of DNA, the central dogma of molecular biology, the deciphering of the human genome, genome splicing and editing, understanding the organization of the cell membrane, structure of proteins and their functions, bioenergetics, the chemiosmotic hypothesis, and ATP synthesis, and more recently, the molecular basis of prion diseases and the role of amyloidogenesis in neurodegenerative diseases. All this happened during my lifetime. Right? All these accomplishments were the result of basic research driven by intellectual curiosity. This, what is basic research? I took this out of a document from the National Science Foundation, and it's important enough that I thought I'll read it to you, because it highlights what basic research is all about. Basic research or fundamental research is the kind of intellectual exercise that helps expand existing knowledge. It is a type of investigation focused on improving the understanding of nature, the laws of nature, or a particular phenomena in nature. This type of research often involves the development of fundamental concepts or theories. Most theories, but most scientists who do the basic research examine data to find the unknown and fulfill a sense of curiosity. Usually, basic research involves the how, the what, and the why questions to explain experimental observations. Basic research looks at how processes or concepts work. Information obtained from basic research often creates a foundation for applied studies, which can culminate in technologies. In this manner, applied research helps to provide solutions to existing problems and meet societal needs. So, why is research important? Without basic research, there will be no new discoveries, ideas, and technologies and knowledge that will fuel the development of technologies. Applied science helps us to bring science closer to the technologies needed for economic development of society. There is also basic research in the applied sciences Oftentimes, when performing applied research, one encounters situations wherein the concepts and fundamentals were not really understood, or the understanding was incomplete or even incorrect. So the opportunity presents itself for the applied scientists to engage in basic or fundamental research. It happens more frequently than you think. Scientists typically analyze a problem under idealized situations. The boundary conditions could be quite different in practical applications and could be quite different, and then discoveries are made. A few examples of science driven by intellectual curiosity and potential application will be helpful in this context. Good idea. Here? Okay. Now take a very simple example. Carbon. It's a very interesting material. All you know that diamond is the sp3 form of carbon. Graphite is an sp2 form of carbon. In the 1980s, people discovered that graphite could be converted into buckyballs, carbon nanotubes, and graphene. C60, or fullerene or buckyballs, was discovered at Rice University in 1985 by Harry Couto, Richard Smalley, and Bob Curl. And they shared the Nobel Prize for discovery in 1996. Single wall carbon nanotubes were discovered in 1993, right, by Don Obuthiam of IBM and Sumio Ejima at NEC Laboratories in Japan. And the diameters of a single wall carbon nanotube is around 4 angstrom to 20 angstroms. Single layer graphene was unambiguously produced and identified in 2004 by Andrei Gem and Konstantin Novoselov. They were awarded the Nobel Prize in Physics in year 2010. An example of research, basic research driven by potential industrial applications. I call your attention, all right, to our process, which is called olefin metathesis. This is olefin metathesis is a method where you take monomers and use an transition metal carbene complex and convert it to polymers. Bob Grubbs, my colleague at Caltech, who incidentally just passed away, developed a series of these catalysts that are really important because they could tolerate many functional groups in the alkene substrate. They're air tolerant and compatible with a wide range in solvents and temperatures. And Bob Grubb shared this a prize in chemistry with Dick Schrock and Ivan Chauvin in 1992. So the boundaries between basic and applied sciences or fundamental applied science are blurred, as they should be. This situation creeps up not only in the physical sciences, but also in the life sciences. So basic scientists do applied research, and applied scientists contribute to fundamental understanding of nature. Example of the life sciences. Jennifer Doudna, all right, a biochemist. When she was a assistant professor at Yale. She solved the three-dimensional structure of the catalytic site of RNA enzyme, ribozyme. In 2012, she and her colleagues discovered the CRISPR-Cas9 genome editing technology that reduces the time and work needed to edit a genomic DNA. This discovery is based on a protein called Cas9 in a bacteria called Streptococcus. And this enzyme is found in the CRISPR immune system of this microbe, and it cooperates with the guide RNA and works like a scissor. All right, this is a picture of the cascade protein, right, and the guide RNA, gRNA stands for guide RNA, and in this particular picture, right, the target, all right, RNA was complementary to a certain region in the double-stranded DNA, and this interaction cleaves, all right, the double-stranded DNA, and in the okay, sorry about that. Okay, this is this pointer does not behave. Okay. Further. Two more. One more. Okay, one more. Okay. Sorry. We don't have a proper device here. Okay, so this technology actually is now widely used for rapid editing of genome RNA in multicellular organizations, from plants, animal research, and to treatment of diseases like sickle cell anemia, cystic fibrosis, and Huntington disease and HIV. And Jennifer shared the 2020 Nobel Prize in Chemistry, right, with her colleague Emmanuel Charpentier. Okay, good. This one, which one is forward? Okay. All right, now, science is not so simple. It's organized into disciplines and subdisciplines. I already mentioned chemistry, physics, biology, and applied sciences. But for each of those disciplines, there are subdisciplines. I won't read them, but there are many. And why is there so many? Because scientists are people, and they're social beings, and they like to group themselves for self-identity. The boundaries between disciplines and subdisciplines have become increasingly blurred in modern times. Why? Because there are more people doing science, greater scientific networking and communications, more borrowing of concepts and methods from one discipline to another, more crosstalk and cross-fertilization. And in recent times, the advances in chemistry and physics and advanced technologies are fueling the development of the life sciences. Not only the life sciences, but also material science, earth science, and atmospheric science. research findings and biological sciences have been generating new scientific issues and materials for study by the physical scientists. The National Science Foundation has come up with a definition of interdisciplinary and multidisciplinary science. I will just paraphrase. When a scientist takes knowledge and methods from multiple disciplines, other than his or own, and works independently on research problems, he or she is doing multiple disciplinary science. Scientists are doing interdisciplinary research when they rely on shared knowledge from different researchers working in different fields. When this happens, over time, a fundamental shift can take place, and you create a new interdisciplinary field. A good example is materials research. If you want to develop a functional and smart material, typically the chemist will have to synthesize material, and the physicist will characterize their properties. And then over time, when they do this enough, right, they will create a new field of material science. And NSF, all right, and people in the field have introduced this picture to distinguish between interdisciplinary research and multidisciplinary research. On the left is independent research when a number of people come together and work on a common problem. On the right is multidisciplinary research when a researcher, right, takes knowledge and information from different disciplines to solve a problem. And these new interdisciplinary scientific we know today, and there will be more as time goes on. A new one that's actually becoming more important is statistical science and energy science. Well, I am a multidisciplinary scientist because I bring the methods of physics and chemistry into solve biological problems. Here's my background. My training was in chemistry and molecular physics. Actually, I got my bachelor's degree in chemical engineering. At the very outset of my career, I elected to take advantage of my background and to apply my training in physics and chemistry and solve problems in biology. It was pretty risky because I knew no biology or biochemistry, never took a course in biochemistry or molecular biology, or even one in general life sciences. But I'm a chemist, a physical chemist all these years, who apply the methods of both physics and chemistry to study biological molecules and systems. But the answer to these questions that I pose are of greater interest to the biochemists and biophysicists and mainstream chemists. And for years, the chemists did not think I'm a real chemist. Now I say that I'm a multidisciplinary scientist. Here's an example of what I recently did since I came to Taiwan. I've been interested in how nature, methanotropes, these are bacteria who survive on methane, how they convert methane to methanol. And I started to work on this in 1992, before I actually came here. And at that time, we know nothing about the protein. So it was a black box. And so we applied different methods of physics, biochemistry, and chemistry to find out where find the active site was. And when the first year I came to Taiwan, I decided it was a tricopper cluster, 3 copper metals working together. And we came up on the basis of that, without the structure of the protein, we came up with a biomimic catalyst, which is shown on the upper right-hand corner. And this artificial catalyst will get oxidized by oxygen and convert methane to methanol. And more recently, we've got this catalyst to work so that it operates better, even better than the enzyme. But just only a few months ago, all right, my collaborators and I work on this cryo-EM structure of the protein, and it's shown on the lower left-hand side of the slide. And what it showed was that the active site is indeed a tricopper cluster. So this is a real triumph of science. Now there are different types of science, which I want to mention, different kinds of research. First, there I call it discovery science or exploratory science. Exploratory science usually begins with asking a question about something nobody knows anything about. Like the question Christopher Columbus asked before he embarked on his journey west to discover America. He had a hunch. So with discovery science, you're stretching your imagination, probing the unknown. You're starting with a black box without any clues of what's in the box. This doesn't mean that nobody has ever asked the question before, and nobody's ever found the answer yet. So sometimes, right, and that was too hard to crack. Science is that kind that's never been done to me. Discovery science is science that's never done before. To me, it is the most important kind of science. Research problems need to be defined, questions need to be asked, and research strategy needs to be developed. Looking at a black box and groping in the dark, high risk and long term, in general high intellectual content, but low productivity. When you start a new project, nobody knows anything about it. You can't write too many papers, at least in the beginning. Opportunities open up new frontiers and new research areas. Usually low competition and not too much literature to worry about. Research for research training of students and postdocs, particularly smart and motivated ones. You train these students to know how to think, how to ask questions, how to define a research problem, how to come up with a research strategy, and execute the work with the highest intellectual standards possible. Okay, we're stuck again. Okay, and then there's mainstream science. That means that the kind of science that everybody's doing. And it's fundamental research driven by recent scientific breakthroughs and fundamentally new ideas by hypothesis, new methods and techniques. A good example, basic research based on discovery of fullerene, carbon nanotubes, and graphene. New methods and techniques such as atomic force microscopy, MALDI and ESR mass spectrometry, and high performance computing, and more recently, artificial intelligence and cryo-EM. These advances are now part of the mainstream science. The topics for mainstream science varies from time to time. When I started my academic career 60 years ago, the issues were totally different. And people don't talk about that so much anymore. They were natural product synthesis, physical organic chemistry, chemical dynamics, surface science, molecular spectroscopy of various kinds, especially NMR, ultra-fast spectroscopy, molecular beam scattering, electron scattering, quantum chemistry. These issues, are now mostly defined and solutions were within reach. The intellectual breakthroughs and paradigm shifts are not expected. And then there's mature science, improvements, further advances achieved by fine-tuning. These are issues largely defined, but understanding can still be fine-tuned or improved by additional experimentation and thinking. Frequently, the issues are revisited with new instrumentation and new methods. A lot of literature to follow. There's a lot of this kind of science can still be performed with occasional paradigm shifts and overturning of existing dogma. But the scientific impact varies. Okay. All right, now I want to talk about basic future directions of basic research. I wish I know. If I knew, I wouldn't be here. The unknown is unknown to all of us. That's why discovery of science is important. But I do know that what constitutes important areas of basic science are worth pursuing. So here's a random sampling of things which I think are still going to be important. Structure and properties of single atoms, molecules, and nanoclusters. Discovery of quantum materials, quantum computing. Understanding collective phenomena. Mechanism of folding of large molecules, including self-assembly. Novel materials, novel molecular systems, particularly those in unusual and hostile environments. Now, novel strategies for chemical synthesis, creating new catalysts to mediate important chemical reactions and to mitigate undesirable molecules selectively. Understanding the effects of impurities and co-catalysts on heterogeneous catalysis. Learning more about how cells of life sustain life and understanding disease states. Educating biological systems to make molecules, not just for themselves, all right, but for us. Designing biological systems to produce fuel, drugs, chemical synthesis. This is a field called synthetic biology. And more recently, the whole field of communication between cells and between life forms. And between bacteria, for example, in your gut, in your intestine. It turns out that these bacteria interact with the host, all right, to prevent diseases and also to affect behavior. I won't go into but in the different areas. So let me conclude then, all right, with a few remarks. Benefit of basic research. Benefits of basic research. Basic research tantalizes the imagination, the human intellect, the human mind. The tangible effects on human spirit and society. Scientific research is becoming increasingly multidisciplinary. Modern science is now a multidisciplinary. All basic and applied science is now multidisciplinary and interdisciplinary. The traditional disciplines of physics, chemistry, and biology have become outmoded. To do modern basic and applied research, we need to train young people to think multidisciplinary and to work multidisciplinary and interdisciplinary. The subjects of and methods to study nature now feed into one another from different disciplines. The principles of chemistry are devised from the laws of physics. All the molecules are the molecules, regardless of where they come from.
It can all be characterized chemically and by methods developed and perfected by physicists. Materials are just molecular systems with unusual behavior between the molecules that form them, so they can be prepared and characterized by the same methods as for individual molecules. All the physical methods developed by physicists, they follow the laws of physics, and all biology follows the principle of chemistry. Basic science will continue to be driven by technology, especially in the life sciences and chemical sciences. Well known to the scientists and those who work in the field of high energy physics as astrophysics. Technologies will continue to be invented and developed to assist basic scientists do their research better and better. However, technology usually lasts no more than a few years before they become displaced by improved technologies. Well, we can look at the development of genome sequencing, methods of structural biology, biological imaging, biological computing, to study biological molecules and their interactions. Their methods evolve over time. Emerging technologies, robotics for chemical synthesis, artificial intelligence in the design of chemical synthesis, and AI in the predictions of protein folding in biological systems. Maybe robotics for genome sequencing and structural biology. Society is now in the fourth industrial revolution. So the question I raise is this revolution affecting the development of basic science? What does the future hold for basic research in the sciences in this area? Most of you know that there are 3 or 4 industrial revolutions. The first one, right, took place in mid 1880s, and it was replacing human power and animal power by water power, steam power, for mechanized production. The second industrial revolution came in the mid 19th century to the early 20th century, and that was the era where electric power came into being to create mass production. The third revolution, or the digital revolution, began in the late 1900s, and is characterized by the spread of automation, digitization through the use of electronics and computers, including the invention of the internet and the stuff for nuclear energy. Now the fourth industrial revolution, that's where we're at, right? We're integrating all of these advances in artificial intelligence, robotics, digital platforms, big data, Internet of Things. The fifth generation is said to be on the horizon, and this is the revolution which will rely on the 4.0 technologies, but the new prediction model where the focus is like on interaction between humans and machines. Yeah, people working along robots and smart machines. It's about robots working with humans working together faster by leveraging the collaboration between the increasing power and accuracy of the unique creative potential of human beings. So we ask the question, is it time for scientists to instruct a machine or robot to do the science, to do their experiment, analyze the data, interpret the results? A lot of data handling and data analysis are already being taken over by the computer. Is it time for the computer, a robot, to design and study and do more of the experiments and more of the thinking? At some point, will the robot be writing the paper, communicating it to the appropriate journal, having a review, accepted and even edited for publication? In my opinion, that is a real nightmare for basic science. So science and scientific research should be fun, what I think. Thank you so much.
Thank you so much, Sunny. All right, so Sunny, now back to the stage. I guess everybody was pretty much inspired by the lecture just delivered by Sunny. Before we move to the Q&A session, let's take a group photo. Now I ask everyone to switch your camera on so that we can take a photo together online with Sunny. All right, if anyone who is not switching the camera on, please do so now. We have a very short time here to complete this important step. Okay, keep doing that. Some of you are not on yet. Okay, everyone. Okay, so please look at the camera there. Okay, so we have the staff member here helping everyone to take the picture. So we'll do that now. Okay, excellent. We are all done and beautifully done. Okay, and the next would be the most exciting part of this event. As you heard from Sunny's lecture, he not only give us the perspectives of research, but also give us a lot of ideas and the very deep thoughts about the next generation of science in the industry. So as I said, now you are free to text your questions on the chat box. I will collect questions from you guys and being responsible to ask Sunny the questions. But before we ask questions from the audience, maybe let me start with a few questions for Sunny as well as Yutai. Both of them are such experienced scientists through the lifetime of career. So Sunny, I guess we can talk about something more, perhaps more inspiring, as many people now join us online are students, master students, PhD students. So would you like to share your idea with them if something really goes wrong in the research and during the career development, there must be some downtime and students may feel very depressed. How to overcome such depression when conduct science?
Well, that's life. Very simple answer. That's life. And people go up and down.
Yes.
But you should not let yourself continually go down. All right. Eventually, bring yourself back up. Okay. And seek advice, counsel when needed.
Yes.
All right. Life is never a failure.
Mm-hmm.
You only live at most 100 years. The oldest man in the world in Spain was in Spain. He died a few days ago, and he was 112.
Mm-hmm.
And that's all you're going to live.
Yes.
Right? So you make your days, your years count. Right? And there's no such thing as a down day or up day. I mean, you just have to keep going, right? Until nature takes care of you.
Yes.
Simple as that.
All right.
But getting counsel is important.
Yep.
Having close friends is important.
Mm-hmm.
Right? Having relationships is important because you, as a human being, you're a social being.
Yes.
and you share emotions, you share thoughts, right?
Yes.
And we all of us, right, move forward together.
All right, thanks. Yutai, you have some words to
well,
give the young generation as well?
Well, to the young generation, sometimes we have downtime. I just go out and exercise and have some hobby. And
Yes.
so, like, I play guitar. I spend a lot of time on that.
Oh, it's wonderful. Yeah.
Going well in my research. That's the way.
Yeah.
Funny say that's life. You don't always go have a good time. You don't always proceed well, and that's part of life.
Sure. Yes. All right. Since both of you have already give the audience some words, perhaps I ask Yutai to give some questions for Sunny, since you guys have been close colleagues and friends for years. So you must have a lot of questions for Sunny.
Actually, I had the opportunity to accompany Yuan Li to go to Sunny's Caltech office 25 years ago.
Yeah.
To invite him to come here. So over the 25 years, we are very lucky. I feel very lucky to have him joining the Institute of Academia Sinica, and as well as in Taiwan. Okay, and he made a lot of contribution to this country, and won this well-deserved presidential award, the highest prize in Taiwan for scientists. And my first question would be that, Sunny, you grow up in a Chinese family in the United States, and your parents, I learned that your parents have different expectation on you. Say your mother expects you to be a doctor, your father expects you to be an engineer, and you end up as a scientist. And so what influenced your decision most? It's not your parent, apparently. It's a professor, or it's a friend, or a peers.
Well, I go a little bit further back than that. When I was at high school, my career aspiration was to be a Jesuit priest.
Oh, wow.
Yes. In those days, I had a dream of being the first Asian pope.
That's a big dream.
Is that because your family also a Catholic?
I'm a Roman Catholic.
Roman Catholic,
right? Yeah.
And I actually went to the University of San Francisco to study theology and chemistry. And at the end of the first year, you'll have to go to a seminary for the summer. And I was too young. I was only 16, 17 years old, and wasn't quite prepared for that solitary life. And I went to talk to a chemistry professor at University of San Francisco, and he recommended that I transfer to Berkeley. He had made the arrangement for me to transfer to Berkeley.
Yeah. And
since my mother is encouraging me to be a doctor,
yes,
I ended up in the College of Arts and Sciences at UC Berkeley.
Yeah.
And I took a course in zoology 100, and the first day I had to cut the sciatic nerve out of a frog, and I gave up. And I went home, and my father said, "Be an engineer." So I went to Berkeley and reapplied to the college, transferred to College of Chemistry, and became a chemical engineer because my father wanted to be an engineer. I didn't know what I was doing, but My father had dreams of me going back to China to build China out of poverty. He always reminded me of this famous bridge in Zhejiang, all right, how important that was. And to being an engineer was really important for the country. And then I did graduate in chemical engineering got my bachelor's degree in chemical engineering. And I did go to Minnesota for a month.
Yeah.
All right, to be a nuclear engineer.
Mm-hmm.
But I came home, Berkeley, to take care of my knee. I had to operate it on, was hopping around Berkeley chemistry department. And I asked the chairman of chemical engineering where I could come back to Berkeley. He said, no, we don't take our own students.
Yeah.
And I happened to run into the dean of the College of Chemistry. And he asked me what I was doing around. And I told him, he says, oh, Sonny, why don't you just come to chemistry? We would love to have you as a chemistry student. That's how I ended up in chemistry. So I random walk. I didn't know what I was doing. I mean, if I had a perceived idea, I mean, my life would probably be very different, probably less boring, probably more boring. All right. As it turned out, it was I lucky. I sort of find, as they say in the U.S., you found yourself.
Yeah.
All right, which is what I did. And when I become a graduate student at Berkeley in chemistry, it was already September, almost October, in fact. And at Berkeley, when you go, when you're in the Department of Chemistry, you had to sign up almost right away. And by the time I started, all the professors taking up their quota, and I couldn't find anybody who would take me because their quotas were filled.
Yeah.
And then there's, I talked to one of the professors, and he said, "Oh, this professor is a sabbatical at ETH in Switzerland. I will take him for you." All right, and you work on my problem for a year, and when he returns from sabbatical, you switch to him. So I joined my professor, Professor Gwynn, in microwave spectroscopy. And he gave me a problem to solve, which I solved in 1 year.
Yeah.
At that time, I discovered the first Quartic oscillator. Oscillators are harmonic. The force field is 1/2 kx squared. A Quartic oscillator is ax fourth power.
You still remember all the details.
Yeah, of course.
Yeah.
I did it myself.
Yeah.
And I just finished that, and I gave it to my professor.
Mm-hmm.
And I said, Raleigh has just returned, and I would go and work for him.
Yeah.
And he said, no, you stay with me. And so I finished with Professor Wood.
Uh-huh.
Now, he seemed to have a strong interest, keen interest in my career. And when I was almost finished, he and Dudley Hirschbach, who was at Berkeley at the time, sort of consulted each other and decided I should go to Harvard, do a postdoc for Norman Ramsey in the physics department, and to learn NMR. NMR had just been in solution has just been discovered and made possible. And he said he should learn NMR by a real physicist, and come back and apply it to chemistry. And I wasn't quite sure that I wanted to do that because I had just gotten several offers from industry. See, you come from a family like mine. Most important thing is to make a living. And my parents, always wanted me to make money. So I got an offer from IBM for $13,000 for cutting details, and I wasn't going to take that offer. And but my professor a few months earlier had encouraged me to apply for a National Science Foundation postdoctoral in physics.
Yeah.
And okay, he's my professor, and I said I'll do it. And then on March 15th, it was announced that I got the NSF postdoc.
Mm-hmm.
And then I had to decide whether I was going to work for IBM or go to Harvard.
Yeah.
And I went home and was cooking dinner. And my father asked me what I was going to do with my life. And I told him, well, I have a few more days and I would tell NSF whether I'll take the fellowship or go and work for IBM. I also got job offers from Lockheed, GE.
Yeah.
I mean, those are the days when you get lots of jobs.
Yeah.
Right? You will be making 13,000, 14,000 a year. Not much. A lot of money in those days, actually. And I told my father, okay, I think I'm going to Harvard to do a postdoc. And my father asked me, how much money are you going to make? I said, $4,500.
Yeah.
And my father looked at me and he said, I have no PhD and I make a lot more money than that.
Yeah.
All right. And I got pretty mad. And I went to Harvard. And it was the greatest thing that happened to me because I finally learned to do science among great people.
Yeah.
All right.
Yeah.
I mean, I was around people like Julian Swinger, Ed Purcell, Norm Ramsey, of course, J.H. Van Vleck. And in chemistry, Bill Klemper, E. Bright Wilson, John Balderschwiller. All these guys, you talk to, you learn something every day, every moment. All right. Even Norman Bloomberger, the laser physicist, you always will talk, right? With, during lunchtime, in the hallways.
Okay, that's afterwards. What I'm saying is that what influenced the professor? Looks like that you don't listen to your parents, you listen to your professor, right?
Or you listen to your heart.
Very strong interest. Unless you have a very strong interest, I want to go to academic. I want to.
Well, it turned out that the person that the most influence on me at that time was W. Hirschbach, who got the Nobel Prize. He had an office, all right, in the same building, and he works at nights, and I also work at nights. And every time I sit down and chat with him. And, I wasn't that interested in education those days. I wasn't interested, to become famous in those days. All right. But he said, I think you will be much happier going to Harvard, all right, than going to work for IBM.
Yeah.
Yeah. When I got the job at IBM, I was going to work for somebody very famous, Remco Clementi, doing theoretical calculations. He was one of the first people to do theoretical calculation of big molecules using his IBM computers. And so I could have been okay, but W. Hirschbach keep reminding me that ideas, new ideas, upcoming ideas that you don't even know about, is what's going to change your life. Yeah. And I thought that maybe, if I go to Harvard, that will, keep me going. The rest of my life.
Yeah. So back to Yutai's question, Sunny, do you think that young people should or will be benefited if they listen to some advices from the senior scientist? Whether that should be the way to cultivate the career?
It depends on the scientist you meet.
Yeah.
I was lucky.
Yes.
All right. I mean, even before that, I have another professor called George Pimentel. who taught me quantitative analysis in my sophomore year. And, you know, knows that I was a very shy boy because, you know, I grew up in Chinatown, and with very, you know, many experiences.
Yeah.
And very shy boy. And George Pimentel said that I was too shy and I need to open up. All right, I can learn to meet people.
Yeah.
All right. And so he opened doors for me.
Yes.
So it's very important, I think, in life to talk to people, you know, who know better than you.
Yes.
All right. And they will offer you advice if they care enough about you. And the hope is that you will meet somebody like that in your life, like I did. All right, with George Pimentel, with Buddy Hirschbach.
Yeah.
All right, and then of course when I went to Harvard, all these big guys always encouraged me. All right, you were, you know, good enough to do great science.
Yes.
And that's when I discovered great science.
Yeah. Yeah. All right. So we just follow what Sunny said, and I deliver two questions from the audience to you, and this must be coming from a student. The first question, I guess the first and second question were asked by the same person. In these days, all the things are moving so fast. Sunny, do you think that young people should still do very basic science in the lab? And what benefits they would receive from the very fundamental basic science? And on the other hand, now artificial intelligence or new technology are coming to the world in such a speedy manner. How do you think about such new fashion? Young scientists also should acquire all this new technology, new knowledge. How do you think about very sort of opposite ideas?
It's a very important question that you're asking. My first response is that life is short, and you should spend your time deriving satisfaction, intellectual satisfaction, from what you're doing.
Yeah.
And the problem with the computers,
yes,
the robots, smart machines, is that they're taking away the intellectual satisfaction you get, all right, from doing something.
Yeah.
And one of my very last slide,
yes,
I was being facetious. I mean, I'm worried about that particular
exactly.
That particular outcome. All right. I think we're relying too much on the computers.
Yeah.
All right. Particularly, you know, for learning, for doing things that intellectual. And we're humans.
Yes.
We're not machines. We're not robots. And therefore, I think we should, you know, remind ourselves that we can derive a lot of intellectual satisfaction from thinking about something.
Yeah.
All right. From doing the experiment in your hands.
Yes.
All right. And particularly if it works. And even if it doesn't work, you learn something from it.
Yeah. Yeah. All right. That's a very sort of answer with the wisdom. I wish this would inspire young students in the audience. And the second question is about the idea to work in the non-academic field after being trained in academic field. How do you think about this career path? Should you encourage young scientists to try that as well?
Well, that depends on the level. If you're a PhD student and
yes,
going, I mean, that's the goal, all right, of your experience at here. Then you'll have a choice. You could go academic, and you go non-academic.
Yeah.
There's nothing wrong with a non-academic career.
Yes.
I mean, some people, I mean, academic career, you have to teach young people, you have to interact with young people.
Yeah.
In a non-academic career, you do not necessarily have to do that.
Sure.
There's room for intellectual growth, professional growth in both areas. It's a different career. That's all.
Yep.
But let me say that when we're training you, all right, to be a scientist for the PhD degree, we're doing one or two things. One is that we're trying to we're trying to create a scholar in you, trying to make you a leader, particularly intellectual leader in society. And that's why it's important, all right, for the professor to train you how to think, how to solve problems, how to lead.
Yeah.
Now, for the other direction that we tend to train young people now for a PhD degree is professional training.
Yes.
I don't think the PhD should be used for that particular type of training. Professional training is training you to learn the skills to do a particular type of job. And it's like training you to be a doctor, training you to be a neurosurgeon, training you to be a lawyer. Nothing wrong with that, right? But that should be a professional degree, and not the PhD degree.
All right. Okay. Thanks. Do you want to respond?
About this, learning a technique, and then you go to the non-academic job. But we will also see that in academic job, there are sometimes also the kind of research that they say they develop, they master some technique. I'm an MR specialist. I am a AFM specialist. So I'm very good at this course.
Yeah.
And I work on. I just define a problem which can use my tool to solve. Okay, and be very good at that particular tool or expertise. And compared to what you've been saying, that you're more interested in the discovery things unknown. Okay, so you think it's good to be multidisciplinary rather than an expert in some specific area?
Now, that's a very good question. If you are a specialist today in something, you will not be a specialist in 10 years.
Yeah.
I mean, simple as that.
Yes.
And so you have to change. All right. So I don't really think it matters where you be a specialist or, I mean, basically, the world is changing so fast that you cannot stay a specialist for too long.
Yeah.
All right. You have to move it. You have to change anyway.
Yeah.
All right. And so my advice is to not think that way, all right, anymore.
Yeah.
Not to learn the skill, not be a professional. All right. Learn to solve problems. Right.
Sometimes solving a problem needs different skills and different tools. So you have to learn, and then when a PhD student, TIGB student, they are all PhD students. They learn something in a lab, and then be very good at a certain tools. To be more versatile, they they have to go to, say, do Star and things like that to be, because when do research, you needed a good tool to solve the problem, right? And then you need to be, nowadays you need to go to, say, different places to learn different tools, technique, and different area. You suggest that, right?
Well, the tools keep changing, keep evolving, right? And so you know, I mean, even the particular tool keeps developing. All right, I work at NMR for many years, and all right, and it kept evolving, and pretty soon I got bored, all right, by
Because
changing.
that was my impression in early days. You were expert in NMR,
Yeah,
using that to solve the structure of the nucleic acid.
yeah, but there are problems that need to be solved, all right, and there will be continue to be problems to be solved, newer ones, more exciting ones, or even more complex ones. All right, and they require different methods, so you have to keep learning new methods.
Mm-hmm.
All right, so it's not for young people. It's not good to box yourself in the field. All right, using a single technique. You have to keep your minds open. All right, that the whole world is yours.
Yes.
All right, to grab all the tools necessary to solve your intellectual problem.
Yeah, that's very inspiring.
And not just intellectual problem, even any problem.
Yeah.
All right. I always tell myself that you don't have to be a scientist or chemist to have an exciting life. I know of a garbage collector who is very creative, and he comes up with different ways of collecting the garbage.
Yeah, certainly.
And he's very inspired.
Yeah.
All right, by me telling him, all right, that he just developed a new way for him to collect, all right, the garbage from my house. All right, so that's what life should be all about.
Yeah.
You should learn to continue to think, to be creative, all right, in the way you live your life. Otherwise, it's pretty boring.
Yeah.
Right.
All right. So, Sandy, talking about the creativity, in addition to the discipline we learned from the school, from the laboratories, do you also learn things from other parts of the life, such as food?
Definitely.
You are the expert of the gourmet food. So, what's the influence of this to your research?
Oh, definitely. When I'm cooking, I'm trying to understand the chemistry.
Yeah.
Yeah,
so that's very true.
Yeah, I'm not kidding.
Yeah.
Why does it form a gel? Why do you use cornstarch?
Yeah.
All right. And so, I mean, you have to always be thinking. All right. I think the world, the problem with the computing world, the robotic world, was we're trying to make people, force people into a mode of doing things, right? And that particular mode is not very inspiring, right?
Exactly.
For living.
Yes.
Many of the problems of society today, in my opinion, are due to the fact that people are no longer thinking.
Yeah, that's a pretty warning sign to the society. But I think what Sunny said is very true. We are all get stuck in a very machine-like world, and everybody now looks pretty similar to each other. Yutai, you want to?
Okay, there's another question. Is that you've been teaching in Caltech for, say, 30 more years, and also you come to Taiwan and it has been here in Taiwan University and teaching there. How do you compare the students in these two countries? I mean, the students in US and the student in Taiwan, is there intellectually different, or there are some other character different, or you have any observation or a comparison or suggestion?
Well, the answer to that question depends on the level. The undergraduates at Caltech are super smart. they have high IQs, and of course they score well. All right, they're sharp, right? But that doesn't make them more productive, they're a better scientist, it turns out. The people who are more better scientists are the people who are more willing to explore, to think independently, have very good communication skills, right? That is something that needs to be, that you people have to work on in Taiwan.
Yeah.
Is to improve the communication skills. Not only in Chinese, but I think not only in English, but in Chinese as well.
Yeah.
In writing.
That's right.
All right. And part of the problem is the education. Here, the education at the secondary school level, by that I mean high school, and even earlier, you're too tied to what's in the books. And the students that that I've interacted with at Caltech, for example, graduate students in particular, they're not so concerned about making a mistake.
Right.
All right.
Yeah, that's a huge difference.
Here, young people, they're, for some reason, because you're scored on, you have to be graded on.
Yeah.
All right. And the only way for you to be successful to have a high score, right? That is what I think is a major problem in the education system here.
Yes.
I think somehow or other, the education system could be reformed so people could be freer to, all right, to learn, express themselves, all right, learn to communicate.
Yes.
Learn to find information instead of having all the information in your head. Or next to you in the book or or the computer even. And because when you're living, particularly when you're doing science, you're trying to solve problems in life, and it's not too different, all right, to be a scientist and to be a human. Right. You're solving problems every day, even when you're not in the lab. It's just a different set of problems, and you have to be creative about it. All right, if you want to be happy in particular. All right. Of course, it's a different set of problems when you're in the laboratory doing research for your professor. So, I think it's mental attitude, which is important in in making people more creative and happy.
Yeah, as you pointed out, I guess the educational system here does not encourage students to face the challenge of making mistakes. Since you have been here in Academia Sinica for more than 20 years, looking through the development of TIGP over the last 20 years, do you think that we have reached to that goal to create the environment here on the campus which cultivates scientists from around the world to examine the questions rather than just doing the same old thing?
Well, I think it's night and day already.
Yes.
All right. All right. But the day is still not the best day.
All right.
All right. So you still got a lot of room for improvement.
Yes.
It's a big change. I came 20-some years ago. There are very few postdocs, no graduate students. And it's difficult to do science. You could do science, but you had to compete with the world. And therefore you cannot do science. And now at least you could talk about, I mean, you have, it's, Academia Sinica is already internationally, recognized research institute.
Yep.
Where you have a flow of ideas coming in and out, not only coming in, but going out.
Yep.
All right.
Correct.
In the old days, if I may say so, no offense to anyone, that the ideas were just being trapped within the room.
Uh-huh. Right.
All right. And so Academia Sinica was more of an echo chamber. All right.
All right.
And so to be exciting, I mean, the young people need to be able to interact with other scientists, right?
Sure.
Doing similar things.
Yep.
That's how they grow. That's how they develop to be international class.
Yes.
Academia Sinica is already international class in many areas now.
Yeah.
All right. And I mean, I'm not sure TIGB has anything to do with it, but certainly having graduate students, having postdocs, and having many of your expatriates coming back, all right, to work makes a big difference. That's quite an achievement already.
Yeah, thanks. Vitai. Further questions?
The question is that you say you kind of categorize the science as discovery-based science, mainstream science. Okay, but you also said discovery science usually is low productive because it's unknown. You don't know where it leads to. But do you encourage, say, a young scientist, like TIGB students, some of them will go to academic. They should engage in this discovery science in the beginning, because in your case, of course, it's different. You already established yourself in certain area, and then you move to other area. But for a young scientist, okay, they should engage in the discovery science, or they go to a mainstream science, because mainstream is the popular science. Like nowadays, everybody is doing these solar cell, so I jump into solar cell, right?
Yeah. Well, it's the answer for me is very simple. All right, and of course, I'm talking about a young assistant research fellow here. All right, I think he should do both. Yeah, he should do some mainstream science, even some, what I call mature science, to get some publication. Because as I say it in Mandarin, 你吃饭, right? Yeah, you need to make a living, get the grants.
Yeah.
But every young person should have some part of the research program, exploratory science. I mean, just to keep your mind occupied, particularly in the way science is being done these days. You have graduate students, you have postdocs, and they collect the data, they generate the papers. But the PI, the professor, needs to have his own science, and that part should be exploratory.
Yes. And
I have always, when I was director of this institute, I always thought that the money, I always set aside part of the money so that the young people could do exploratory science. Yeah. Not for the other kinds.
Yeah.
Presumably they could raise it from other sources.
Mm-hmm.
All right. Because it's the exploratory science that at least has the potential or the opportunity to lead to something big.
Mm-hmm. Yes.
All right. Particularly for the individual.
Yeah.
It makes him unique.
Mm-hmm.
And that's very important.
Yeah.
All right. The problem with academics in Taiwan is that everybody wants to be everybody else.
Yeah.
All right.
That's correct.
And that's not the way it should be. You want to be yourself.
Yeah.
All
Yeah.
right.
But that also, when you compete for a grant from the National Science Council, they have certain areas. They say these areas are important areas. They expect you to easier to get a grant if you're working on some of the popular topics, right?
Yeah, that's right. But I think, Moss should set aside a certain part of the budget for exploratory science, long-term science.
Yeah. Yeah.
All right. I mean, it doesn't take a lot of money to
Yeah.
to explore.
That's right. That's right.
It takes a lot of money to turn the crank. I'll tell you. All right.
Yeah.
So much of the science in Taiwan is just turning the crank,
Yeah.
putting what I call the whole stock room through the machine.
Yeah.
All right. But that's that kind of science does not generate necessarily new ideas. All right. To move the field forward, it generates papers, generates data,
Yeah.
generates publications, and you could put that on the list, and your supervisor would get promoted.
Yeah.
But I think that's the professor, the PI, has the responsibility to himself.
Yeah.
All right. To keep to do exploratory study, to keep his intellect moving.
Yes.
Instead of just being a research supervisor.
All right. Right. So Sunny, your words just links to the next question from the audience. I guess the environment in general in academia sinica in Taiwan is still not perfect yet, for sure. So one question coming from the audience was asking you, is there any good suggestions to the society here to welcome scientists, scholars from different backgrounds, from diverse backgrounds, who wish to settle down their career in Taiwan? What should we do more here in order to attract people from other areas in the world?
A very interesting question, which
Yeah.
this morning I was discussing it with somebody.
Yeah.
An open society is better for Taiwan.
Yes.
All right. And I mean, you have you need to bring in more people to have a workforce soon, because you're running out of your own people.
Exactly.
All right. And so, and the only way, for people who want to do that for you is they have an opportunity to, all right, to even stay and immigrate to the country.
Yes.
The U.S. has benefited greatly, all right, by this strategy. All right.
Right.
I mean, my father went to America from Guangdong. They have absolutely no education. They've never been to school.
Right.
All right. And I got the opportunity, all right, to develop. I mean, it was lucky because that people opened doors for me.
Sure.
All right.
Yes.
And that was very important to me, of course, but at least had the opportunity. I don't think I'm the only one who experienced that kind. All right. That experience in America. A lot of people have.
Yeah.
And this, I think, enriches the country.
All right.
I think that's very important. You cannot totally rely on your own people anymore.
Sure. Yes. Right. Yeah. That's a very fair advice to academia sinica and to Taiwan as well.
Yeah.
Yeah. So certainly we should work together to open up the society.
Yeah. Well, I mean, part of the reason why I created TITP the way I did, all right, was to improve not only the way you do science here, but the culture, the people culture.
Sure.
Right. And people could exchange ideas.
Yep.
One very simple thing: the average graduate student in academia sinica, their ability to speak English has improved. I mean, many many hundredfold because of the program.
Yes, exactly. Yes, and also encourage Taiwanese students to communicate in English because their colleagues, their friends, are people coming from other part of the country, other part of the world. All right. I guess our time is pretty much up. So lastly, I really want to represent everybody join us online to thank Sunny and Yutai for this very interesting and interacting forum. We got a lot of questions from audience as well. And I think this is well done today. And also thank the organization to host this event. And certainly thank everyone joining us online. Without your participation, this event wouldn't be so beautiful. All right. Thank you, everybody. And have a good day. Take care. Bye-bye.